Hello guys, welcome back to Chemistry Digest. On today's topic, we're going to be talking about electronic configuration of elements and ions. But for the purpose of this video, we're just going to talk about that of the elements first. Then I'm going to leave a link in the description for you to access the electronic configuration of ions. Alright, let's dive right into it. So here is a table showing the first 20 elements with their electronic configurations. So what is electronic configuration? It is simply the arrangement of electrons in the different shells, subshells, and orbitals of an atom. It shows how many electrons are distributed around the nucleus. It is important to note that there are three rules that must be obeyed before filling electrons into orbitals. The first is the Avbau's principle, which talks about lower energy orbitals being filled first. The second is the Pauli's exclusion principle, which talks about two electrons occupying each orbital with opposite spins. And the last but not the least is the Hund's rule, which talks about electrons occupying empty orbitals first before pairing. So, the method of the electronic configuration to be used is the subshell notation, and these are the requirements. First of all, you have to get the atomic number of the said element. The second thing on the table is the order of filling. The third is the subshells, which we also call the sublevels, the SPDF subshells or sublevels. Then the maximum number of electrons in each subshell. Now, let's start with the first thing on the agenda, which is the atomic number. Now, this table shows the first 20 elements in order of the atomic numbers alongside the electronic configuration. I hope you also recall that atomic number of any element is equal to the number of protons of the said element, which is also equal to the number of electrons of the element. For example, in sodium is the 11th element. It has 11 protons and also 11 electrons. The only time the number of electrons change is when the atom becomes an ion. We will discuss that when we talk about the electronic configuration of ions. Alright, moving on to the second requirement, which is the order of filling. We are going to employ Avbau's principle here, which states that electrons are fed into orbitals in order of increasing energy levels. So it is imperative you learn this table and the order of arrangement from 1s down to 7p, as it shows us the sequence of which the order is gotten from. Hence, while filling electrons into orbitals, we follow that sequence, that is from 1s, 2s, 2p, 3s, and beyond. And finally, we have the subshells and the maximum number of electrons. So in the S subshell, the maximum number of electrons it can contain is 2, while in the P subshell, the maximum number of electrons it can take is 6. The D subshell takes a maximum of 10 electrons, while the F subshell takes a maximum of 14 electrons. So how do we know this? First of all, we have to acknowledge the fact that S, P, D, and F subshells have 1, 3, 5, and 7 orbitals respectively. How? S has 1 orbital, P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. Let's imagine orbitals as rooms where electrons will occupy, right? According to Pauli's exclusion principle, one orbital can only contain 2 electrons. That is to say, 2 electrons per orbital having opposite spins. So if S has 1 orbital, and for each orbital 2 electrons can only enter, then it implies that it will contain 2 electrons. Alright? Now let's take a look at P subshell with 3 orbitals. If 2 electrons can only enter each of them, we will have a total number of 6 electrons at the end of the D. If we use that same logic for the D and the F subshell, we'll have a total number of 10 and 14 electrons respectively. It is also important to know the shapes of the orbitals of the subshells. The orbitals in the S subshell are spherical, while those of the P subshell are dumbbell shaped. D orbitals are clover shaped or double dumbbell in shape, while F orbitals are multi-lobed or are said to have complex shapes. Alright, let's solve the first problem of the day. We are asked to write the electronic configuration of sodium using orbital notation. First, like we discussed earlier, we write down the atomic number of the element. In this case, it is sodium. And of course, sodium has the atomic number of 11. So once we acknowledge that, we move on to the second agenda, which is to fill what? The 11 electrons into the energy levels, starting with the least energy level. And also bearing in mind the maximum number of electrons that can be allowed in such energy levels based on the subshell it carries. I hope that makes sense. Alright, looking at the energy levels, we are going to start with 1s. And remember, the s in the 1s means the s subshell, and it must contain 2 electrons, as long as we have not exhausted the 11 electrons available, which is coming from sodium. Alright, so the 1s is the first energy level, and it is going to take what? 2 electrons from the available 11. So when it takes 2 electrons from the available 11, we're going to have a remainder of what? 9 electrons. We now move to the next energy level, which is the 2s. It also has s, right? So s will take up 2 electrons from the remaining 9, and we are going to have a remainder of what? 7 electrons. On to the next one, which is the 2p energy level. The 2p has p, alright? So it's going to take what? 6 electrons from the available 7. I hope it's making sense. So now, at the end of the day, we have 1 electron left. Alright, so that 1 electron is going to be taken by the 3s energy level, making it 3s1. Alright, so at the end of the day, we are going to have 1s2, 2s2, 3p6, and 3s1. Fantastic. So at the end of the day, you will notice that they shared the 11 electrons accordingly based on the maximum number of electrons the subshells are allowed to carry till the 11 electrons that are available is exhausted. Alright, solve these other questions and leave your answer in the comment section. I'll leave a link in the description for the electronic configuration of ions. Do well to like, subscribe, and share this video to your colleagues who may need them. Until then, see you in the next video. Bye.